Hi, I'm Shawn Billings of Billings Surveying and Mapping in Stumpwater, Texas. And today we're going to be talking about JAVAD GNSS JField software localizations. We're going to be looking at that within a known coordinate system. A localization in JField does one of two tasks, performs two different tasks. The first is it determines projection parameters for an unknown coordinate system. So this is useful when you're working with a coordinate system that isn't really related to the planet Earth, such as a 5,000 type system with assumed rotation and coordinates. The second is that it determines transformation parameters between two known coordinate systems. So this would be useful for determining the transformation between survey started with an autonomous base, and then you want to relate that to existing control points that are also on a known coordinate system, such as state plane. It's also useful when you're looking to determine a transformation between two coordinate systems. Now, regardless of which type of localization you're doing, there are keys to success with either one. First and foremost, you want to have your base always in a suitable location, free from visible obstructions to satellites and away from buildings and trees and structures, things like that. You only use fixed solutions, fixed RTK solutions, no floats, no standalones. Then you want to set your control or select control points that are in suitable places, that they're free from visible obstructions to satellites, and that they have good geometry related to your project site. You want to use precise, undisturbed points. You want to use points that don't have that aren't fence posts and things like that, or bent rods. And then you also want to make sure that those control coordinates are reliable. Where did they come from? So first, we're going to look at a single point localization. It's probably the simplest one within a known coordinate system. Here we are on the JField home screen, and we're going to select Localize in the upper right corner of the screen. All right, now then, in the upper right corner, I've got NAD 83 2011 Texas North Central Zone. This is a state plane coordinate system with NAVD 88 vertical heights. On the left, I've got my system set to an unknown coordinate system at the moment, but we're not really concerned with that. So on the right side, under the surveyed points, I want to add a point. I'm going to add a single point. This is a point that I surveyed in. All right, and in the coordinate list, I've got it set to surveyed points, not design points, but surveyed points. And then I'm going to select S0001, just stands for surveyed point number 1. It's just my own nomenclature on this. So I select that and recall it. Now on the design side, we're going to add a single point, and we're going to select it from the list. Now notice I'm going to toggle over to design coordinates. These are non-surveyed points, things that were entered or imported. All right, so I've selected point 1. Now I need to make an association between S001 and point number 1. So I touch the screen and highlight both point numbers. And then I press the manual button so that I can select what sort of association that I want. Now, if I didn't have good elevations, I would just simply select horizontal. But in this case, I've got a good elevation from my control point, and so I want to go ahead and fix it in 3D. As you can see, we could select a horizontal, and we suddenly have a vertical residual. But in this case, like I said, we're going to do 3D. The residuals are 0 because after the point has been translated, there's no difference in the coordinates. So that's to be expected that we'd have zeros. When we select setup, it shows us the parameters, the transformation parameters. We see that from the north origin to the north ground, that's going to be our translation in north. Our east origin to east ground is going to represent our east translation. Rotation is 0 because we have no baseline to rotate to, and the scale difference is 0 because we have no baseline to scale to. North inclination and east inclination are also currently 0. Because we held the point in 3D, we've got a vertical offset of minus 10.9027 feet. That's the difference in the autonomous base coordinate that I started with and the actual coordinate that I want to fix this survey to. Now, single point localization can be dangerous because we have no redundancy built into this. So we want to make sure if we're going to do a single point localization that we're sure about our coordinates and that we're very sure about our monument that we're using to make sure that we've got the right coordinates, the right monument, and that we're set up on the right point. With that done, it should be okay. But again, it's risky because there's just no redundancy to verify that we have good results. So with that done, we're ready to exit out of this screen and return back to our main localization screen. And then we're going to hit save on the bottom right and save this localization. We'll hit save localization parameters and then give this localization a name. I would recommend naming it something that has some meaning or significance to you. I'm going to call this 1 point local. And here we can see the translation parameters going from the north origin to the north ground, same for the east. We see, again, we've got a rotation of 0 and a scale of 0 and a vertical translation. Now, it's very important that we re-import our design coordinates. Our design coordinates currently are considered state plane, and we're surveying theoretically in state plane. But in actuality, one of these can't be state plane. Localizations provide us with a useful fiction. That is, that they allow us to pretend that we're on a state plane system when technically we're not, because the latitude and longitude that is underlying the state plane system is still based on an autonomous position. So what we want to do is re-import these points by going into files, and we're going to import them again as our local system. So let's press Files, Data Exchange, and Import. Now I'm going to import my text file. I'm going to skip the header. And I'm going to re-import these points, but I'm going to be careful this time to change the coordinate system for the page that I'm importing into to 1 point local instead of state plane. Now it's set up there, but let's go ahead and see how we do that. Press the coordinate system, navigate to that local system we just created, and select it. And then we're going to import into that page. So rather than these being treated as state plane coordinates, they're being treated as this offset system. And now we've got these points imported in. One last check, let's make sure by going into COGO inverse, an inverse between our surveyed point and underlying design point that agrees with it. We should see 0. And here we have point 1 to S0001, ground distance of 0, delta height also of 0. So we've proved out that our localization has worked and the coordinates are all on the same system now, and we're ready to work. All right, so that was fun. Let's take it up a notch, and now we're going to look at a multi-point localization in a known coordinate system. So we're going to be selecting several points this time. So we're back on the home screen of the Triumph LS, and we'll go back into Localize. And we want to set our coordinate system back to NAD83 state plane, which is our underlying coordinate system. All right, so now we're going to add several survey points. We want to toggle over to Survey from Design, and we see the list change. And now we want to just go through and we're going to quickly check points. Just use that check hardware button on the side and use those scroll buttons, the navigation buttons on the side to select your points. So we've got 1, 2, 3, 4, 5, 6, 7, 8, and 9. Then on the design side, we want to do the same thing. So we're going to add design points that correspond with those surveyed points. All right, and now we want to make the association between these points. So I'm going to highlight point 1 and highlight point S0001, and I'm going to fix those in 3D. Next, we're going to select point 2. The check, whenever it's not fixed, is shown in gray, and anything that's fixed shows in blue. So right now, we're going through and we're going to select all these as checkpoints just to see if we have any obvious outliers. So I've got 1 point fixed in 3D, and because the coordinates I've imported are state plane and the coordinate system I'm working on is state plane, I should have pretty decent agreement just off of that 1 point. So let's see what we come up with. All right, so notice that up there in the first row, 1 and S0001 have a residual of 0. This is because it's only a single point and it has no residual after the translation. It's a perfect translation. Now, with a single point, we've got no rotation and no scale determined. This is just simply based on translating these coordinates. In a known system, we shouldn't expect to find any rotation. State plane north is state plane north, or geodetic north is geodetic north. So there's no need to determine a rotation. Same for scale. There's no reason to need to determine a scale if we know that the coordinates are both related in the same way between our survey and our design. But we've got no redundancy with that kind of a setup. And so it's better to have multiple points tied in so that we can verify our results and have the kind of redundancy we need. With all of our associations made, let's take a look at how they check out. Point 1, of course, has 0 residuals, as we discussed. Point 2 looks really good, 1,000th in northing and about 700ths in easting, a couple of hundredths in elevation. 3, similarly, has very low residuals. Point 4, that one looks a bit high, doesn't it? 13 thousandths and 67 thousandths. We probably need to scratch that one from our localization. Those residuals are just much higher than what we're seeing and what we should expect. So let's keep looking. Point 5 has reasonable residuals, and point 6 also has really good residuals. So let's take a look at the second page, and we'll look at 0.7. Yeah, 0.7 doesn't look very good either. 1.8 feet. So we need to mark that and take that one out. Let's see, 0.8 looks good, and 0.9 looks good. All right, so we've seen that 0.4 and 7 have really high residuals, and we should not use those in our localization. We should probably investigate those points and figure out what's going on. Could we have located the wrong point? Were we given a bad coordinate? Did we have a bad shot? Or was the point disturbed? We need to check. But once we remove those, now we can add our good points into the localization and use everything. Now that we've checked with a minimally constrained localization, we can start to add those points in and fix them both in horizontal and vertical and let them contribute to the localization as well. Going to the second page, we're going to skip 7, leave it as a check so it doesn't contribute anything to the localization. So now we've got all of our good points working into the localization. And you can see that the residuals have dropped down quite a bit by doing this. Much lower than they were before because now they're contributing to the solution. All right. So anytime you're doing a localization, always go into the setup to check and see what is going on. How did the localization turn out? You should know what you should be expecting these parameters to be so that you know what you should be expecting. We're working in state plane and we're localizing to a state plane system. So I should expect the rotation to be 0, and I should expect the scale factor to be very near 1. The biggest difference we should see will be in the north, east, and up because we started with an autonomous position. So we should expect a few meters, possibly, several feet in translation because of the difference between autonomous and our real world coordinate. So inside setup, let's take a look. Our northing difference, just subtracting the north origin and north ground, is about 5.3 feet. Doing the same with the east origin to east ground, we've got a difference of about 3 feet. That's realistic for an autonomous to real world coordinates. And then the vertical, about 10.9 feet. Rotation is very close to that 0 we were expecting at 11 seconds. And our scale difference is very close to 1, having only 13 parts per million. So this is a good looking localization. Now you can switch it from parts per million to a ratio to make it easier for your viewing, just according to what you'd prefer to view it in. The north and east inclinations are something that we really want to pay careful attention to. These values can be dangerous because, like any rotation, it depends entirely on the geometry. So a short line with a large angular rotation is to be expected. But if you take that short line and you extend it out a long distance, then that large rotation begins to really accumulate. That's what could happen with this east inclination. We see that we have 150 seconds in that eastern rotation, and that could really accumulate to some high values later. Now, The good thing about having an inclination is if the geoid model in an area is poor, then this localization can account for that. Particularly if you've got some good precise level data or something like that, determining orthometric heights in the neighborhood, it can be beneficial to use this localization and include the inclination heights. But you want to make sure that if you do, you're working off of good elevations with a good spread across your network. And we'll take a look at some more of those pitfalls in just a moment. Let's keep going. Anytime you're using these inclination values, it's important that you don't go beyond the polygon that you've established, because these control points are not very far apart east and west. The corridor that I've got in this localization, it's not difficult to accumulate that 150 seconds of east inclination. One of the things that I appreciate about JField is it gives the user the choice of what parameters in these localizations to keep and which parameters to override. So our rotation and our scale actually should be 0. We've seen that with these 11 seconds that it's very close to 0 just by observation, but we're going to force it to 0. And we're going to force the scale difference in parts per million to 0, which is a perfect 1 in scale factor. And then the north inclination and east inclination, we're also going to set to 0. By setting that rotation and the inclination and the scale to 1, now we're just left with a translation. We're only changing north, east, and up with this determined transformation. So this is going to cause the residuals to increase because we're no longer looking at a best fit. We've taken out some of the parameters that made it into a best fit. And the reason that we've done this is because north is defined by the projection and the GNSS constellation. So it's proper for us to zero out that rotation. North is north. Because the vertical control was not exceptionally precise, we'd be better off to trust our geoid model and remove those tilt values as well. Now, by removing those tilt values, we've increased our useful range of our localization because those tilt values are not going to give us a problem out at longer distances. So now we can go back to our main localization screen and we'll see that those residuals have increased ever so slightly. But overall, we've still got a really good localization. Looking at page 2, we see that we've got great residuals there as well. All right, before we continue in our little example, I've sent the crew back out and we've resolved the issue with our point number 4 and our point number 7. I'm going to delete that that survey coordinate for 4 and for 7, and then I'm going to add the newly observed value, the new surveyed value. And the crew named that S004_T, and the same for point number 7, S0007T. And now we're going to match those up as check shots and verify that the newly observed coordinates are proper. And we're going to do the same for 7. And let's check those out. Okay, those residuals look very good. They look really low. So it looks like whatever the issue was with those points in the field, we've got it squared away now, and we could incorporate those into our localization. All right, I'm going to go ahead and save the localization at this point, and we're going to change that name to something meaningful for the project. I'm just going to call it 9-point local. Now we will want to import our coordinates, as I showed you earlier, as that into that 9-point local coordinate system. One of the interesting things about the localization is we can add points to that localization once we've saved it. What that will do is just modify our transformation parameters and change up the way that the grid of imported points connects to our coordinate system. So let's go ahead and add a few points. Let's see, to start with, we'll go ahead and go to multiple points, and we're going to add S1101, S1102, S1103, and S1104. Then on the design side, we'll need to do the same thing, and we're going to add 1101, 1102, 1103, and 1104. Now we'll need to make the associations between those 4 points. So let's take a look at what happens when we select the wrong points. All right, we notice that immediately everything goes to red. We've got horrible residuals throughout the localization. And even though everything's horrible, look at 1101. It's really bad. Everything else is in the 50 to 80 foot range, but 1101 is in the hundreds of feet range, which tells us it's the most likely culprit in our localization. So we know that that was most likely our culprit. Let's try putting it with the right point this time. We'll select horizontal, and everything's back to blue again. Now then, I've intentionally used a different height reference frame for these points as I did the initial points, so that we can see the effect of some vertical difference between points in a localization. It's going to have some pretty significant impact on us, so let's take a look. But you'll notice that we've got some pretty high residuals. Now, these aren't necessarily normal survey residuals, but I've intentionally degraded our vertical accuracy for this example. All right, so I've got 1101, 2, and 3 set as checkpoints, and we see that horizontally, 1 and 2 look pretty good, but point number 3 is looking pretty rough all the way around. Looks like it might have been displaced somewhat. And even though the elevation is off on 1101 and 1102 by about 17 or 18 hundredths, 1103 was about 27 hundredths. So it's probably going to be one we'd want to leave out. All right, now 1104 looks pretty reasonable at 100th, 8 hundredths, and 18 hundredths. So it's kind of consistent with what we saw with 1101 and 1102. But 1103, again, just looks a bit out of kilter with the rest of the points in our localization. So we'll want to ignore that one. All right, so now we're going to go in and check our setup. And I want to see what would happen if we allowed that north and east inclination to take effect. Now, we previously we zeroed everything out and forced it to our expectations on our transformation. The way to get our calculated values back for our rotation and scale is just to undo those check marks, go or select OK, and then go back in, and we see everything's returned back to those calculated values. So 11 seconds, 13 parts per million, etc. Now let's take a look at what that's done to these points that are out just a little bit further from our original localization. We see that it's really corrupted those elevations. Now we're, instead of 1800ths, we've got in excess of 2/10, and 1101 and 1102 are actually in opposite directions, 2800ths and 2500ths. So we've kind of teetered like a seesaw with our vertical. So let's take a look and kind of play around with this just a little bit. What I want to do is go into point 1104, and we're going to fix it for horizontal and vertical. My goodness, look at what it's done now to point 1102. We've got 8/10 of vertical difference now from what it should have been to what it is. All of this because we had about a 17 or 1800th error on that point. It's fairly close to the corridor of our original, so a little bit of movement close to that corridor really kicks those further points up a lot. And my goodness, look at that east inclination at 234 arc seconds. Very likely to be our cause of problem right there. All right, so now I want to fix point 1102. It's the one with the really high residual there of 85 hundredths. Let's fix it in horizontal and vertical also and see what now becomes of our vertical residuals. All right, so now we're back to 1101, showing a residual of about 16 hundredths. 1103, as we'd seen before, it looks to have been displaced, and 1104 is now showing a residual of about 17 hundredths. What does all this mean? Why are we seeing these kind of big swings in our vertical? Well, we need to consider our point geometry. So let's take a look at the map here, and we see that 1102 is off of this corridor of points to the west. Zooming in, we see that point 1104 right there is very close to this corridor. So a little tiny vertical difference really kicks that tilted plane up by the time you get over there to 1102, which is what was causing our change. It's maybe 300 or 400 feet off the corridor. 1104 is maybe 50 feet off the corridor. And so if you tilt just a little bit at 1104 at 50 feet, it turns into a big amount at 1102 there at 400 feet from the baseline. So this is why it's just terribly critical that you're mindful about how you use those tilt values. Like I said earlier, generally speaking, you're better off zeroing out those tilt values, in which case then the vertical translation just becomes a simple translation. There's no rotation involved. The exception, of course, being if you've got good vertical data that you've run in with a level and it's well distributed across your project and a good geometry, and you're not extending beyond that leveled data. So now, just like before, I'm going to zero out the rotation, zero out the scale, and we're going to fix everything except for 1103. We're going to fix it to the horizontal. And we see our residuals for these additional points really coming down once they start to contribute to the solution themselves. So horizontally, including those points, and we've set our rotation back to where it can be calculated. With those longer baselines, now we're at less than 2 arc seconds and just a few parts per million in distance to get the best fit. So we've got enough points horizontally, at least, to really show that we've got a good localization. I'm going to go ahead and zero those again. And at this point, we go ahead and save our localization and ready to continue work. Now, it's important when we export our points in our line work that we use this localization coordinate system for our export. Otherwise, all of these points and lines are going to be related to our autonomous base coordinate. Remember that localization provides us with a useful fiction. So when we export, we want to make sure we export using this localization, and then our coordinates will mimic true state plane coordinates related to our known coordinate values that we've localized to. So be sure that when you export, that you export in that way. So this has been localization with a known coordinate system. We've looked at single point, and we've looked at multi-point, and we've looked at adding points after the fact to improve our localization. Few things to watch for, but it's a really powerful tool. It's really powerful for being able to verify the uh, the way that multiple points compare with a design system or a known system of values. If you're retracing a survey, you can use this localization as a quick, powerful tool to see how well your points agreed with each other. Just a lot of utility in there, and it's real valuable for you as a user to know.